Welcome everybody. Today we'll be looking at quantitative mass spec. And what we'll do is we will look at ion quantitation. We'll look at parameters affecting ion yield. We'll look at relative quantitation. This is for species of similar size and charge. Also relative quantitation of species of dissimilar size and charge. We could look at relative quantitation in complex mixtures using heavy isotopes and also label free. And then we'll look at absolute quantitation of small molecules. But before I begin, I'd like to introduce you to this gentleman. This is Sir Edwin Southern, FRS. 20 years ago, he was my boss. And Ed told me in absolutely no uncertain terms that mass spec was definitely not quantitative. Well, I can tell you that in the last 20 years, experience has proven me right and Ed wrong. So I'd like to dedicate this presentation to him. So let me give you some idea of why Ed said that. If we want to quantify something, if you want to quantify a physical constant, say take something like protein concentration within a sample, you would quantify that by UV absorbance perhaps. And this is how you do it. You do it through an HPLC system, and you would measure the intensity of the UV, and the quantitation is totally straightforward. The reason for that is you are making a direct measurement of a physical constant. So that's the UV absorbance. The quantitation is completely straightforward. And what Beer's law will tell you is over a certain range of concentrations, the greater the concentration, the greater the UV signal, the higher the concentration. And the only thing you need to assume is that your HPLC peak is pure. Of course, it might not be, which is a good reason for using mass spec. But provided it is pure, Beer's law is very effective. The situation in mass spectrometry is completely different. You are not making a direct measurement of anything. What you are doing is you are making an indirect measurement of the number of ions that arrive at the detector. And there are a whole load of variables which can affect this. The first one is this: there will be a variable source current. This depends on the nebulizer, and the source current will vary. It can vary throughout the experiment. Also, when we have, I'm just going to try and get a pointer. Also, inside the source, there will be competitive ionization taking place. So some species will ionize preferentially over others. Once we get into the ion optics of the instrument, different ions will have varying degrees of ion transmission. So some ions may be transmitted more efficiently than others. When they reach the detector, there is again variable detection efficiency depending on what those ions are. You can see saturation of the detector, and you can also see part of that is a nonlinear detector response. So there are a whole range of instrument variables that will affect the efficiency of measurement. What that means is the greater concentration of your sample, it may or it may not result in a higher detector current. You can quantify multiple species, multiple MZ species within a complex mixture by multiple reaction monitoring, and we'll look at that. And also you have the advantage of you can experience attomole sensitivity for small molecules by MS quantitation. The other factors which are going to affect the ion yield is you may well experience losses in your HPLC. There may be a nonlinear response, and this is going to be dependent on the column and also the solvents you use. And also you can experience contamination for carryover from the HPLC column. So let's have a look at ionization efficiency. If you are working on small molecules, and I've defined those as anything below 600 Daltons, what's going to affect the ionization efficiency is the acid-base strength of what it is you're analyzing. So you can have compounds of similar mass, but they can have different pKa, and they will ionize to different extent. Above 600 kilodaltons, it's a different situation. The ionization efficiency is going to be determined by the surface area. So polymers with a greater surface area will acquire more charge, and they will ionize more readily. Instrument polarity will affect the ionization efficiency. Normally, instruments are operated in positive ion mode. The reason for that is because they're more efficient in positive ion mode, and most species will preferentially ionize in positive ion mode, but not all. So some species will ionize more efficiently in negative ion mode. We are also going to experience, or could experience, ion suppression from contaminants. So various ion suppressing agents would be plasticizers within a solvent, polymers, salts, detergents, and also non-volatiles. All of these things can quite dramatically reduce the ionization efficiency to the point where there's nothing to measure. We're also going to experience ion suppression from anything that coelutes with our sample. This is an issue when you're doing analysis of peptides. If you have several peptides eluting at the same time, you may find that you have a preferential signal for one over the others. Also, we're going to experience differences in desolvation efficiency. So the more efficient your desolvation, the better, but the variables here are going to be solvent composition, which is going to change throughout an LC-MS run, the solvent flow rate, nebulizer pressure, counterflow gas flow, and also counterflow gas temperature. And all of these things can affect the ionization efficiency. So you might assume that if you spray an equimolar mixture of something into the mass spectrometer, you would see an equal response. So you might expect to see peaks of equal intensity. And you don't. You definitely do not. There are various reasons for this. One of them is acid-base effects, others surface area effects, and also size effects. So the size itself, it does not affect the ionization efficiency, but the larger your MZ species, so the more charge, the bigger it is, the more difficult it is to transmit it through the ion optics. So what that means is that high mass species, they will have a very low velocity and they are very difficult to detect. And I'm trying to illustrate this with three spectra here. So these are spectra of some small molecules. It's an equimolar mixture of 6 tripeptides, and you can see you are experiencing different ion intensities for these 6 species. It's a lot more dramatic when you go up the mass scale. So here's an example of moldy data. This is polyethylene glycol. It's an equimolar mixture of 1, 2, 3, 4, 5, 6 different size classes of PEG. And you can see that the detection efficiency falls off a cliff. It's basically inversely proportional. It's an exponential decay in detection efficiency for this species. You can observe exactly the same thing with proteins. This is an equimolar mixture of 4 different proteins. This is insulin. This is effectively a peptide. It's a small protein, cytochrome C, larger protein, trypsinogen, and then BSA. And you can see, again, the detector efficiency falls off exponentially with mass. So it's not simple to do quantitative mass spec. There are some technical obstacles. You just need to understand what these are to overcome this. but it's worth doing because there are enormous advantages of mass spec detection over other detection techniques, and there's huge progress being made in this area in the last 20 years. So let's start with something quite simple. So if we have species with a similar size and charge, we can do relative quantitation. So I'll give you an example of this here. These are proteins. These are phosphoproteins, and this one is the same species. It is SMAD1, and we have 3 phosphorisoforms here, the phosphorylation state 0, P1, and P2. And the differences between these 3 species are actually extremely small. The difference in mass between those 3 species is only 0.3%. The difference in charge between these species, you can't see this from this data, but the difference in charge is only 2%. So these 3 species are almost identical. And what that means is we can make a relative quantitation between these 3 species. So it's perfectly valid to say that phosphorylation state 0 is 6% of the sample, phosphorylation state 1 is 74% of the sample, and phosphorylation state 2 is 20% of the sample. And you can do the same thing in experiment 2. You can quantify these peaks relative to each other. However, what you cannot do is you cannot say that this peak is greater than this peak. You cannot do relative quantitation between these two experiments. Basically, these species have to be within the same spectrum for you to do this relative quantitation, and comparison between this experiment and this experiment is invalid. You can also do relative quantitation of species which are different, which would have dissimilar size and charge. And one example of this is label-free quantitative proteomics. So in proteomics, quantitation is absolutely essential. If you cannot achieve accurate quantitation, your proteomics data set is useless. And this is an example of label-free quantitative proteomics, and it uses this value, EMPAI. And so this is a metric that is basically based on the intensity of individual peptides, and they are compared against the intensity of a standard set of peptides from a digested BSA at a variety of standard concentrations. And what it allows you to do is you can relatively quantify your sample relative to these BSA standards. So it can give you an absolute quantitative value, and you can compare samples from one experiment to the other. However, it assumes that your protein is going to behave exactly as the same way as BSA, and it won't, because protein digestion and peptide ionization is highly variable. So the release of peptides from BSA is not necessarily going to be as efficient, or it may be more efficient than it is with the protein that you're interested in. And so, although this is useful, you can compare one sample with another. You shouldn't really use this for absolute quantitation because it can be out by an order of magnitude. So if EMPAI tells you sample A is more abundant than sample B, that's fine, but I would not use it for absolute quantitation. It's basically an extremely approximate quantitation. Why should you use it? Well, the reason you should use it is because basically it's already there. If you do a mascot search, you get this data. If you drill down into the mascot search results, it will calculate this for you, whether you need it or not. So it's just there and you can use it, which is very useful. If you are serious about quantitation, you probably want to use a labeling technique. The earliest labeling technique, or the earliest reliable labeling technique, is SILAC. I would say all the proteomics experiments before this probably I would regard as complete junk. I think SILAC probably the very first reliable quantitative tool for proteomics. So what SILAC stands for is stable isotope labeling of amino acids in culture. And it's very simple. You begin with your two experimental conditions, and you add either a light isotope of an amino acid or a heavy isotope of that amino acid to your two different experimental groups. So here you have a control group, here you have a drug-treated group. You will lyse them both separately to quantify the protein, and then you will combine them together. When you do your separation, any losses will be comparable from one sample to the other. And when you do your mass spec, you will see that you have a mass separation which corresponds to the difference in mass between your heavy and your light isotopes. So you can program the instrument to look for this isotope mass shift in a particular peptide, and you simply compare one species against the other to get your ratio of intensity. So that's SILAC. Another method of relative quantitation of species with dissimilar size and charge is rapid fire. So rapid fire, you can use this to measure enzyme kinetics. So what rapid fire is, it's simply a fluid handling robot. And what it does is it will perform 3 solid phase extractions in parallel, and it will allow you to load these into the mass spec. So you'll have clean and desalted samples, and they can go directly into the mass spec by flow injection. So you can couple this instrument to any Agilent mass spec. Typically they sell this with a triple quad instrument. It's a bit more sensitive than a QTOF, and it's also cheaper. So this is your rapid fire robot, and the data that you will get is you will get a single extracted ion chromatogram for all the injections you have made. Okay, so it doesn't make an individual file per injection. You have one file for the experiment which contains all the injection peaks, and the relative abundance of one or perhaps several different species can be monitored over time. And so this is what the data looks like. This is an example of a data set from lysine demethylase, and we are losing. So this is for conversion of a histone peptide. So this histone peptide is demethylated twice by this enzyme in the presence of 2-oxyglutarate, and here you can measure the enzyme kinetics at different concentrations. So that's all relative quantitation, but you can also use mass spec for absolute quantitation. And absolute quantitation of small molecules is absolutely standard in DMPK. So what we'll look at is sample preparation. We'll look at pairing standard curve. We'll look at what you need to do for internal calibration. We'll look at you need quality control. We'll look at multiple reaction monitoring and quantitative data analysis. So sample preparation for this type of work is very, very important. So you can quantify small molecules and metabolites in biological fluids. Typical biological fluid would be serum, but they are very, very high complexity. There's usually a huge amount of protein and DNA and lipids that are going to interfere with your analysis, and you need to get rid of them. So the way to do that, there are different ways. It can either be done by precipitation and ultrafiltration, or it may be done by solid phase extraction. In our lab, we do it by solid phase extraction. You can do this in relatively high throughput. What you will end up with, so the solid phase extraction will remove all the high molecular weight species which you're not interested in, and ideally you will left with low molecular weight species, peptides and metabolites. However, your sample complexity is still going to be extremely high, and you are still going to need a purification technique, a preparative purification technique before you go into the mass spec. So this is usually done by HPLC. One problem with any type of purification that you do is if you are looking to quantify something, if you have done any type of purification, you can expect concentration dependent losses. So what that means is you must have some type of internal standard, and we'll talk about that in a second. But even though you've done your HPLC purification, your sample complexity is still going to be extremely high. So the way we can deal with this is through a technique called MRM, or multiple reaction monitoring. So the idea behind this is you still have a complex mixture of ions. You select the ion of interest by virtue of its parent ion mass. You would then fragment it, and then you would then measure the intensity of a specific mass of a fragment. And the technique is called multiple reaction monitoring because you can do this on several different compounds at the same time. You are going to need a standard curve, so you will prepare a standard curve from a known concentration of your analyte. From the standard curve, you can calculate the limit of detection. You can also you will establish the point where there is detector saturation, so you will have a linear region within your calibration curve, and also you will have a non-linear saturated region at the higher concentration. You will need an internal standard. This is to compensate for all the different variations, or all the different variables that we described, all the instrument variables, and also losses that you will experience from purification and concentration. So you will need a known concentration of an internal standard, and you need to spike your sample with that internal standard. You would do that to your calibration standards, you do that to your samples, you would also do that to any QC standards that you have. So with your internal standard, all measurements are normalized with respect to the internal standard. And so you can allow variations due to sample preparation, ionization, and ion transmission, and these can be corrected for. However, your internal standard, in order to behave this way, it has to have exactly the same chemical properties as the target compound. But you need to do this, it needs to be separately quantifiable. So in practice, the only thing you can use to do this is a heavy isotope. So you need to have a heavy isotope of the compound that you want to quantify. Just at this point, I would say, we don't use radioisotopes. Radioisotopes aren't really desirable in mass spectrometry, but also they're not necessary. You can acquire, you can achieve a very high degree of sensitivity using stable isotopes, heavy isotopes, and they're not really necessary at all. yes, I don't really like people talking about radioisotopes in analysis, simply because they're not necessary. You can use heavy isotopes in their place. It's much safer and it's a much better way of working. So in multiple reaction monitoring, what we do is we isolate the parent ion of interest. We isolate its master charge. We're then going to fragment it, and then we're going to quantify a targeted fragment of that MZ species. So the parent master charge and the fragment master charge are going to be unique for that compound. There may be multiple compounds in your sample with the same parent ion mass, but once you've fragmented it, there are going to be very few which have a fragment mass from that parent ion. So what this means is you can have multiple compounds, in some cases, as I'll show you, with the same parent ion mass, but they will fragment differently and they can therefore be quantified simultaneously. So your internal standards are quantified simultaneously, and because you are using MS1 to isolate the parent ion and using MS2 to isolate the fragment ions, the spectra that you end up with are virtually noise-free. And so MRM is something like 2 orders of magnitude greater sensitivity than MS1 quantitation. So here's how it works. We start with an MS survey scan. This is our survey scan, so we have different MZ peaks. We will identify those. We will select precursor 1. We'll fragment precursor 1. We'll then select precursor 2, fragment precursor 2, select precursor 3 and fragment that, and then we will return back to doing the survey scan. So this is the MRM duty cycle, and I'll show you an example of this with this compound. So this is glibenclamide. This is a sulfonylurea drug. It's used to treat type 2 diabetes, and it inhibits type 2 potassium channel within the pancreatic beta cells. And we did this work as part of this clinical trial. So this is our analyte. This is glibenclamide. This is the parent ion mass, which is 496.4. So when we fragment it, there is a mass transition, so we lose this compound, and we end up with a transition mass of 369.0. This is our internal standard, and this is deuterated glibenclamide. So it has a deuterated hydrogen here, and so it is 11 Daltons more massive. When we fragment it, we lose this group and we end up with the same species. Okay, so the species that we are measuring, the fragment, is the same mass, but the parent ion are different. So we can quantify these two species separately. And this is a result of the glibenclamide analysis. So what was happening here is, I think there were 16 patients given the dose, and we collected serum samples at different times following the injection, and you can see the buildup of the glibenclamide within the patients over time. Okay, so this is 8 glibenclamide doses over 8 separate visits. So another thing you can do with MRM is you can use it to measure multiple analytes, and this is an example of using MRM to measure different neurotransmitters. So these are the neurotransmitters within this sample, and what we're able to do is use this compound to label them. So this compound is able to label different amino acids, different neurotransmitters with different to generate our internal standard heavy isotope, and in a single LCMS run, we can therefore quantify 7 different compounds simultaneously. So that's all I want to say about quantitation. Just to say that what we're doing in mass spec quantitation is we are measuring the yield of ions which reach the detector. We've looked at the different parameters that affect that yield. We've looked at relative quantitation of single species. We looked at relative quantitation of different species. We've seen how you can use heavy isotopes for relative quantitation. And then finally, we've seen how you can use heavy isotopes for absolute quantitation in multiple reaction monitoring. So that's all I want to say, except that please join us next week. We have the third of our invited speakers. This is Professor James McCulloch from the Chemistry Research Laboratory, and he's going to be talking about an introduction to metabolomics. I'm going to finish here. I'm going to stop sharing my screen. I'll be very pleased to answer your questions. If you would like to use the chat function, please be my guest. Okay, it doesn't look like we've got any questions this time, so okay. We've got a question. I've heard of PRM, parallel, but not MRM before, so is there a difference between these two methods following detection following reactions? Parallel reaction monitoring. I'm not sure I know the answer to that, Ben. I would guess that it's a similar technique. Yes, I think it's probably a similar technique, but I'll have to look that up. I don't know the answer to that, Ben.
I might be jump in here.
Yeah, please do.
So parallel reaction monitoring is performed on FT instruments such as Orbitrap, so you acquire all the transitions in parallel.
Mm-hmm.
It's essentially which technological platform that you use. Whereas in
Yes.
MRM, you kind of go for the transition one after the other. In principle, all the basic principles are the same, except for the acquisition.
Okay, thank you very much, Thierry. Do we have any more questions, please?
Rod, in rapid fire, there's just one injection at a time, right?
There is one injection. Yes, you're right. Yes, so yes, it's not strictly parallel purifications. What's happening is the purifications are happening. They're happening in series, but they're overlapping. So as one purification begins, the second purification is already underway. What that means is that yes, you can basically make your flow injections. Your flow injections are happening faster than the rate of purification. That's the point I was trying to make, Oleg.
Okay, so basically you purify 3 samples at the same time, in a sense.
Well, yes, but they are at different stages in the purification.
Yeah, they
cycle.
just follow each other on the column.
Yes, yes, absolutely.
Okay, thanks.
Yeah. Well, if there are no more questions, thank you very much for listening, and please join me next week to hear James McCulloch, and thank you very much, and I will end the meeting.